I'm going to tell you all about this project we've been working on called Pangeo Forge, whose goal is crowdsourcing open data in the cloud. So just starting off, I want to acknowledge a bunch of contributors to this project. Above all, Charles Stern, who is a software engineer in our group who's been working full-time on this project, and almost everything you'll see here is really credit due to him. He couldn't be here right now, but he'll be here for the sprints. And a lot of other folks, and also I really want to thank NSF for funding this. They gave us $1.5 million for this project over 3 years, and that sounds like a lot, and it is, but now we're realizing, you know, it's really hard to build end-to-end data platforms, and it probably actually costs a lot more than that to do this right. Okay, so what's the vision here? Ben gave a great talk about open science at the keynote yesterday, and you know, I would summarize the open science vision, the way I see it, with this pseudocode. We would like everyone in the world to be able to verify and extend all of our scientific knowledge. Okay? This would really be transformative for the world. It would allow so many more people to participate in the scientific process, and it would make discovery go much faster. So what are the barriers to realizing this vision? There's a lot of course, social and economic and political barriers. In terms of the technical barriers to open science, we tend to think about reproducibility in terms of 3 elements. The code, in order to reproduce a sort of data-driven scientific result, we need the code, we need the environment in which to run the code, and then we need the data that the code acts on. And I think we're in a pretty good place right now for open science. We have a lot of tools that can meet all of these needs. We're very good at sharing code today. I don't think there are a lot of barriers to just getting your code out there. And we got a lot of great tools for creating and sharing environments. And we can argue about, you know, which of those tools is the best and whether package management in Python is really as dysfunctional as some people say, but I think there's a lot of things that work, and this is more or less solved. And likewise for data, there's a lot of great data repositories. Now in science, we have a big emphasis on fair data, DOIs. We have great data repositories, things like Zenodo, Figshare, Dataverse. But in my world, we're not quite there yet with data sharing. That's because in my field of oceanography and climate science, our data is really big, and we're doing data-intensive science. So we can't just put, you know, petabytes of climate model simulation like in Zenodo, right, and just download it every time we want to reproduce a result. You know, I think this sort of data-intensive scientific workflows are really common today in a lot of different fields. You know, they're open-ended analysis, exploratory. We're sort of iterating a lot on the data, and that's how discoveries are made. And so, you know, I really don't think that we have a good solution for sharing big scientific data sets on a global scale. What happens is that privileged institutions, rich institutions like my university, Columbia, we create what my colleague Shel Gentleman likes to call data fortresses. Right? So we've got like a supercomputer in our basement, you know, a big cluster. We download a bunch of data, we store it on that computer, and we can analyze it, and our group has access to it, and we can be productive this way. Have you ever gotten some code from someone? They're like, oh yeah, here's my code. And you know, the first line is open up the data files, right? This is like where reproducibility stops. These local file paths are just, they're not part of a global namespace that everyone can access. And so then if you really want to reproduce the result, you got to like get all that data off of that cluster or something. Raise your hand if you've had this type of experience. I'm curious. Okay, so this confirms my hypothesis that that's pretty common. So here's sort of what I characterize as some problems with the status quo of how we interact with data in science. First of all, we have this emphasis on files as a medium of data exchange. And that's, you know, of course, like this is almost obvious. Of course we're exchanging files, but data is not files. Like files are just one way we can encode data, and this emphasis on creating a lot of files creates a lot of scientific toil around processing and organizing those files. Contrast this, say, like if you have a database, and it's just like you can just query it directly. You don't really think about what are the files, right? There's a lot of data wrangling involved in scientific workflows, but that's rarely collaborative, right? We collaborate on developing software or interpreting results, but we don't, this data work kind of happens in the shadows. If it's data-intensive science, it's pretty expensive to do. So you need infrastructure. You need a big supercomputer, you need a big cluster, you need cloud computing resources. This is limiting participation in who can do this type of work. And finally, this data fortress problem, really, limiting access to outsiders is a feature, not a bug, of the way our infrastructure works. Like, they're literally designed to keep people out, which is the opposite of what we want to do in an open science sort of collaborative world. So that's a real limiting factor. So within the Pangeo project, we've been trying to prototype what it looks like to do cloud-native scientific data analytics. Okay, and this is just a different way of working based on the cloud computing paradigms. And there's three main elements that we emphasize when we talk about cloud-native scientific data analytics. One is analysis-ready cloud-optimized data. I'm going to actually spend most of my talk talking about this. I'll unpack that in a little bit. Two is data-proximate computing. So we've heard a lot about Jupyter already today, and I think for a lot of scientists, just having a Jupyter notebook sitting next to your data gets you 90% of the way there for so many workflows. That's just such a powerful and simple paradigm for how to work with big data. And then finally, if you have really big data, you want to have some sort of elastic, sort of scalable, distributed processing that you can deploy to scale out your analysis. And all of these elements are readily available in a sort of commercial cloud environment. We also think it's really valuable to sort of separate the storage side from the compute side. Right? So in our HPC centers, we are very much, they're tightly coupled storage and compute, right? It's part of the same system. The cool thing about the cloud is we can put our data in cloud storage, and someone else can come and compute on it with their budget in their account. And that's a really, that's also kind of a paradigm change, and it's completely different from this sort of status quo scientific infrastructure. Okay, just unpacking our stack a little bit more. How do things work in Pangeo when we're doing cloud-native data analytics? We tend to use a storage container format called ZAR that it stores data directly in object storage like Amazon S3. Then on top of that, we run Dask, which helps us scale out our analysis and really leverage the throughput of that distributed storage system. And then we use Xarray and other higher level packages to sort of provide a user-friendly interface or API to our data. Now, a key part of making this workflow work well is something I call analysis-ready cloud-optimized data. Okay? So when we're dealing with analysis-ready cloud-optimized data, we're really able to think about the data set as a whole and not like what files it happen to be sharded into. So that's a huge cognitive load. And when we have access to analysis-ready cloud-optimized data or analysis-ready data, that allows us to sort of skip that tedious data cleaning step, right? And you all know what this is if you do analysis. It's great to have analysis-ready data. That's when the fun part of scientific work begins. But getting there takes some work. So, in Xarray, this is what analysis-ready data looks like. We've got one big data set. It's full of really rich metadata that tells us what the different variables are and how to interpret them, and it's chunked in an appropriate way that makes it amenable to the analysis we want to do. Now, cloud-optimized is the other part of this. What is cloud-optimized data? Cloud-optimized data is compatible with object storage. In the cloud, we fundamentally try to avoid the file system as much as possible, store data directly in S3, where it's accessible over HTTP. And so we want to be able to do lazy access and intelligent subsetting of our data without having to just download the entire data set. And that's what cloud-optimized formats allow us to do. So probably the most well-known one is something like Parquet, widely used for tabular data. And in sort of array world, we would use something like ZAR or TileDB or one of those formats. Now, if you can get cloud-optimized data, you can make your analysis really fly. So here's a figure that shows the sort of throughput we can get working in Google Cloud Storage on analysis-ready data as a function of the number of parallel, processes we throw at our analysis. And, using this type of architecture, we can pretty easily process data with modest levels of parallelism, like 100, different workers. We're processing data at 10 gigabytes per second. So you can really do big data analytics this way in a relatively simple way. One of these curves, let's see, the red one is Open Storage Network, a new cloud storage federation that lives outside of the commercial cloud. It's operated by NSF-sponsored computing centers. I'm gonna come back to that. Okay, so this is awesome. We have this stack, we have these formats that allow us to do this, data-intensive science really fast and collaboratively in the cloud. Problem is, making this analysis-ready data is really hard. It's a lot of labor involved in going from archival formats to the analysis-ready cloud-optimized formats. You have to figure out where the data is. You have to know all about these formats and how to produce them. You need a place to stage all of this data and generate your analysis-ready data and then upload it to the cloud. And then finally, you have to know how to analyze it, right? Now, who should be doing that? Whose job is it to make this analysis-ready data? Well, some say it's the data provider. I don't really think it's the data provider's job to make analysis-ready data. I think the scientists are the right people to be making analysis-ready data because scientists know what it means for the data to be analysis-ready. So this is what Pangeo Forge is all about. The goal of Pangeo Forge is to allow anyone in the world who wants some analysis-ready data in the cloud to produce that data set without having to have a lot of specialized knowledge or a lot of resources. It's directly inspired by Conda Forge, right? Conda Forge really democratized and opened up the production of Conda packages by creating a cloud automation platform that just made it so that anyone could contribute a recipe for a Conda package. So we're explicitly trying to copy that pattern, but with data. So the Pangeo Forge project consists of two main parts. There's Pangeo Forge Recipes, which is an open source Python package. You can think of it as an ETL framework that allows us to specify how to extract data from archival locations, transform it, and then load it into cloud storage. And then we have Pangeo Forge Cloud, which is an automation platform that allows you to run these recipes in the cloud automatically and integrates with GitHub. So Pangeo Forge Recipes is just a standalone open source library that you can install and run it anywhere. You can use it on your cluster, on your laptop, anytime you want to try and build some data. Pangeo Forge Cloud is it's basically a SaaS platform that we're building. How does Pangeo Forge Recipes work? Well, I'll show you a demo soon, but basically we start with something we call a file pattern that describes where source files live and how to get them. And then we combine that with a sort of storage config that tells us where we want to put the data set. And we put these together into a recipe that also contains any sort of transformation or processing steps we want to know the way. And Pangeo Forge Recipes compiles these down into many different distributed execution frameworks. So currently we support execution using Dask, Prefect, and Apache Beam. And it's relatively straightforward to add different parallel execution frameworks to this if you want to run it some other way. The way Pangeo Forge Cloud works is it basically plugs into GitHub. It looks for these recipes in GitHub repos, and then it runs them in the cloud using something we call a bakery. And it stages and it puts the data into the cloud storage. So the vision here is that we can use GitHub as a collaborative platform to work on these data recipes. And so rather than doing this data work, alone in the shadows, we can bring it out into the open, and also we can just have one copy, like for everyone in the world, of the data because it's in the cloud. Okay, so at this point I'll switch over to a demo and show you what the contribution process is like for Pangeo Forge. Can you just tell me how much time I have left because we started late and I didn't get a timer? 10 minutes, perfect. Okay, so here is how the contribution process starts for Pangeo Forge. I make a pull request to a stage recipes repo. Does that sound familiar to anyone? We copied it directly from Conda Forge. What does that consist of? Well, there's two files in here. Just like in Conda, we've got a meta.yaml that tells what our data set is, a bunch of metadata. Here I'm importing data from the NOAA Global Precipitation Climatology Project. This is a data set that is daily observed precipitation from all over the globe. And here's some metadata about who owns it, what's the license. NOAA doesn't make the license on their data clear. They just say no constraints on data access or use. That's not actually a license. But we do the best we can to document the license and the provenance of the data. Here's the actual recipe. Okay, and this is some code using Pangeo Forge recipes. And basically what this code does is crawl the NOAA website, figure out what all the files are. There's about 10,000 files that go into this recipe. I'm not going to really walk through the code too much, but basically we just turn this into what we call a file pattern, and then we create this xarray zar recipe object. It's really one line of code, basically, sending in this pattern and a few customization options that I developed along the way to make this data set come out a little better. I submitted that as a pull request to Stage Recipes, and that initiated a validation process wherein a bot starts talking to me and telling me that I didn't do it right. So it gives me some suggestions for how to fix the recipe formatting. Then it creates a test version of this recipe, a small version that it tries to run, and then it finds, oh, you have another typo in your recipe, fix it. And finally I fixed it, and it tells me that my recipe is now running, and then it succeeded. And it actually gives me a link to how I can open the data directly. Because this is in the cloud, this data is immediately public. And we have a binder, I'm not going to open this now, where we could open and run it. Once this pull request gets merged, this goes into a new feedstock repo, just like Conda Forge. All of this is visible and accessible through the Pangeo Forge website. So if I go click on feedstocks, now that this PR has been merged, I can navigate over to this this feedstock I just created, and I can see this GPCP, Global Precipitation Climatology Project. You can see I've got links back to the original data providers. I have the license information here. The maintainer is me, we can see, and that links back to my ORCID. And now the great thing here, these are sort of logs of the recipe runs. I won't go through this right now. The great thing here is we've got the data set. So I can open this up, just copy this, and I can just start working on it. It's in the cloud. It's been run by the automation system. So I'm going to go over to a Jupyter notebook I have running here. This is a 2i2c managed hub. I'm going to run this code, and I'm going to open this data set. So what was started as 9,226 individual netcdf files that I would have had to download from NOAA, because of this I can open the data set in about 2 seconds and have lazy access to the entire thing. And we can make a plot. We can look at the precipitation plot. Let's get just the first value there. Right, so this is, let's make this a little bigger just so we can have everyone have a look at what's in here. So this is a precipitation field over the globe. We're not really trying to make a map here, but you can tell the contours of the data. And because we're in the cloud, we can really scale up our processing. So I'm going to try and do a little live coding here. I'm going to first from Dask Diagnostics import my progress bar. And then, now I happen to know this data has some corrupted values. I figured that out, and we don't really know why it does, but I opened an issue for it over in the feedstock. Right? So this is what collaboration looks like. I found there's some corrupted values in the data set. Now we're tracking that, right? We'll fix it. But in the meantime, I can look at the data. I want to make a mask because I know precipitation shouldn't be negative, and I know it shouldn't be greater than, let's see, I want values that are greater than or equal to 0 and less than, say, 1,000 millimeters per day. And now I'm going to calculate the climatology of global precipitation from the entire data set. So I'll say precip climatology equals ds precip where mask mean over time. And I'll compute that. Oh, and let's put that with the progress bar. With progress bar. This is just X-ray and Dask in the cloud, which you've probably seen a lot of examples of so far. So, and this is no cluster here. This is just a couple threads on my in my notebook. 6.8 seconds, I calculated the climatology of this entire data set. Let's plot it. Plot, that was a little too big, so let's do maybe 10, 5. Oh, my mask didn't work. Greater than or equal. See, awesome. Oh, and I gave this a really weird size, 10.5. Okay, the perils of live coding. So this is the global climatology of precipitation on Earth. It's a fascinating figure. There's a lot of science in here. Some features that stand out are the intertropical convergence zone near the equator, which is has the heaviest precipitation on Earth. We can see the sort of mid-latitude storm tracks over the Gulf Stream and the Pacific. We can see the southern hemisphere storm tracks. So, you know, this is a scientifically fundamental figure that represents a synthesis of everything we know, our best understanding of how precipitation happens on our planet. And now it's accessible to everyone in the world to do this type of analysis instantly, rather than having to download 10,000 netcdf files before they can even get started. Okay, so I'm going to switch back to the talk and finish up. Okay, so where are we at with this project? Who's seen this video, right? So this project is way, way harder than we thought it would be. If you really zoom out and think about what I propose we're going to do, to create essentially a cloud-based mirror of all scientific data, that's, you know, we're crowdsourcing that from everyone in the world, and none of us really know at all what we're doing. We can write Python code, but this is a lot more than just Python code. And so, you know, it's going okay, but there's a lot of work left to do. We've done a ton of learning. And by the way, the person in this video is literally Charles. This is his job to push these things through and fix things that break. Things are breaking all the time. It doesn't quite really, it does work, but it doesn't always work. Right? So Pangeo Forge is live and open for business. If you would like to get data into the cloud, come to the website and you can try to do it. There's some challenges we've identified. So these recipes often have 10,000 or more tasks. This is really just the number of files we generally have to ingest. We're currently using Prefect as our workflow engine, and we're finding it's just not really working at that scale. So we're refactoring the backend to use Apache Beam as our execution engine. We're also finding data has a lot of edge cases. You know, there's just every data set has something new that trips up our code, that trips up our system. And we're addressing those, but the scope is potentially very large. So despite those challenges, we're really excited about the potential of Pangeo Forge to transform how scientists interact with data. And we invite you all to get involved. If this is exciting to you, you know, come join the project. You can either contribute to the software, you can contribute recipes, and we'll be organizing a sprint on Saturday to create more recipes and populate this repository. You saw there's only about a dozen data sets in there right now, so it's not comprehensive in any way. So I think I'm out of time, and I'll stop there, and I'd love to take questions if there are some. Yeah, are there limitations on the data that you can upload? So first I'll say this, you don't upload data. There's no way to upload data to Pangeo Forge. Instead, Pangeo Forge has to pull the data from wherever it is. And that's deliberate. We're not trying to create an archival repository. So the assumption is that the data already exists somewhere else that is accessible over the internet. So that's one point. Now, we connect with Globus, so if the data are on a system that has Globus, we can pull it through Globus, so that means we can. We also focus right now on the most common data model in the climate, ocean, weather sciences, which is multidimensional array data that we can load with Xarray. There's a lot of tools out there that serve the tabular data sort of ETL space. You know, if you want to do ETL on tabular data, there's things that can help you with that. So that's where we haven't focused. So right now, basically, you need to be able to open the data in Xarray for it to work with Pangeo Forge. Going forward, we might expand that to include tabular data or other data models, but that's not our priority right now. Yeah, so just like Pangeo Forge, like the recipe contributions are moderated. Like you can't just ingest any data. And we explicitly require license information as part of the recipe, just like Pangeo Forge. We won't let someone distribute data that's not licensed to be distributed openly and that's not licensed to be copied. So if it has a CC, Creative Commons type license, which most open data does, this is perfectly allowed, provided we link back to the original data provider, which we do. But I mean, this is only for open data. Like if the data is not open, Pangeo Forge is never going to support sort of like authentication or private data. It's like an open science project. So that's sort of a bounding box I'd draw around it. Yeah, so what you're describing sort of hints at all the possibilities that exist. We could imagine dependencies among this data. So I imagine I want to create a data product that's derived from precipitation and some other thing. Right now, you can pull, the only requirement to ingest data is that it be on the internet. So if it's in the cloud, it's on the internet, right? So you can absolutely build on the data that's in the repository. We don't explicitly track the linkages between data in Pangeo Forge yet, but that is absolutely possible, and you could imagine a whole graph of relationships. Those are the sort of things that are possible once you have this type of system built. Yeah, that's a great question. How do you search and find data in this repository? So right now we've only got like a dozen feedstocks and maybe 50 data sets in there. So you can just browse through them all. And our priority has been to just make that basic layer work. We plan to have a catalog and search on the data. We are going to use the spatiotemporal asset catalog framework, which isn't necessarily appropriate for all data that might be ingested, but it's kind of the best framework that we have, and it has a lot of traction. So we'll have a stack catalog and a stack search endpoint, so you can discover data through that. Great question, yeah. The question was, are we going to be able to accommodate near real-time data, or sometimes people would call that streaming data, data that is continuously updated? The answer is it's definitely on the roadmap, and I think we have the pieces in place to do that, but we don't support it now because it just introduces another level of complexity, and we already kind of are. It's just, like I said, it's really hard. But this is kind of why I'm giving this talk. We need help. That's something we want to support. It's technically feasible. We're really just limited by sort of developer effort at this point.